Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Module 11 is all about network design. So we're going to be talking about the hierarchy structure, the scalable structure, and we're going to be talking about the hardware, both of the router and of the switch. So let's go ahead and jump right on in. Hierarchy network. So essentially, there is a 3-layer model, and I know there's supposed to be a video, and that's if we're using the packet tracer, the Netacad training. It's inside their training, but we're just going to go ahead and do it this way. So we have a top layer, we have a middle layer, and we have a bottom layer. The bottom layer is called access, middle layer is called distribution, top layer is called the core. So this is going to be, the core is going to be like our layer 3 switches, and those are going to be the more expensive switches. Underneath our core switches will be distribution switches. This may be like a classroom or a building type switch. And then our distribution switches will actually then have access layer switches. These are going to be more of the dumber switches. This is also going to be what's going to connect to our end devices. Our end devices are in the access area. Core, distribution, access. And again, normally how we do this is the core is the most expensive, distribution is the second most expensive, and access is the cheapest. Now we're going to have designs throughout this entire lecture covering this. So we do this design because it's scalable, because the network needs to be able to scale or to grow as the network grows. So as the organization or the business, as it grows, we're going to have to talk about things like, can it support its critical applications? Can it keep pace with the different diversity of the business needs? Can we centralize the management of the different layers? So as we've grown throughout the last 30 plus years, we've also got a newer concept called borderless switching networks, and that is now looking at different branch locations and how they tie directly into our different LANs. So the borderless switch network provides the framework to unify wired and wireless access built on a hierarchy infrastructure of the different hardware that is both scalable and resilient. Resilient means it can recover, it can be damaged and still be functioning. Borderless switched networks are very hierarchy, they're very modular, they're very resilient, and they are flexible in nature, meaning they can adapt based off of the requirements that are being thrown at them. The hierarchy model, again, 3-tier versus 2-tier. 3-tier, we have our core, distribution, and access. Here is our access groups. Here's our core groups. Our distribution groups in the middle, access groups are on the bottom. Where 2-tier basically collapses the core and distribution into one layer, and access is by itself. In most of these Cisco design models, you're going to see access layers by themselves. So how do we define the layers? The access layer provides network access to the end devices. These switches are going to connect to the distribution layer switches and handle just basic connectivity. The distribution layer is going to implement routing, quality of service, security, and other layer services. It will also aggregate the large-scale wiring closets, and it will help to limit layer 2 broadcast domains. Normally, distribution layers switches are going to be a layer 3, and that's why it can handle certain routing features. Again, a lot of the frame control or a lot of the network shaping is going to happen at this layer. The distribution layers will connect the access layer devices to the core layer devices. Again, the core layer being the top layer. So the distribution layer will act as an intermediary. The core layer is the network backbone, and it will connect to several layers of the different networks. The core layer also provides basically fault isolation and high-speed backbone connectivity. This is going to be the most expensive area of those switches. So essentially, let's say we have a 7-building campus. Each building will probably have its own distribution layer, and each floor of those buildings may have their own access layer. We have our core layer that actually interconnects all of the different buildings. And again, here's another example of how we would be designing that. Here we have multi-building locations, each building having their own distribution, and inside each building they have the stacked access. Again, typically one access per floor, one access per room, kind of just depends on how you're looking at it. If we do a 2-tiered model, we will have our core and our distribution kind of collapsed, and from there we'll have each floor being their own separate access networks. And again, within this network design, we're not talking VLANs, we're not talking aggregated links, we're just talking the general overview of how the network would be designed. We would typically, if we are doing this type of an approach, also have additional segmentation at each floor for the appropriate functionality based off of VLANs. But for now, that's outside of this general scope. So the roles of our switched networks, again, core, distribution, access. You're going to notice that distribution and core typically use layer 3 switches. Access will only typically use layer 2 switches, and that is it. So switched LAN will allow additional flexibility and overall management, allowing the higher level functions in the core and distribution to handle things like traffic management and other features of the switched network. A switched LAN will also support wireless network connectivity and other technologies like phones and mobility-based services. So let's go ahead and let's dive into how we designed the network to be scalable. So in previous chapters, we talked about things such as link aggregation, we talked about redundancy first hop protocols, we talked about wireless connectivity, we talked about different types of scalable routing protocols. So all of those go into the design for scalability. Essentially, to define scalability in the terms of the network, it is the ability to grow without losing the availability or the reliability of the network. So the designer, the network administrator, whoever is actually laying out the design of the network, has to develop a strategy to enable the network to be available and scale as it grows. One of the big issues here is it's not one of those things where you can plan for today's use. You have to plan for tomorrow and future use. And again, we do that through the redundancies, multiple links, like link aggregation, routing protocols, and wireless technologies. All of this allows us to plan for additional growth. And as we're planning for that growth, we also have to plan for redundancy. That way, if a link goes down, we don't have to worry about loss of connectivity. A single point of failure means bad network design typically. However, sometimes it's also a cost. If a link goes down, it may cost X amount. However, to have a redundant link installed may be an additional cost, which is going to be the cheaper route, and that also has to factor into the network design. Also, redundancy also means duplicate equipment, and some organizations may not have the ability or the capital to install duplicate equipment. So again, trade-offs. So when we're providing failover services, normally we're looking at the most critical devices first. If our core goes down, it means the entire network could be going down. So maybe if we can only afford redundant equipment in one area, we set up redundant equipment at our core level first. And I've actually worked with organizations that were fairly well off, but financially would not justify the additional costs for redundant equipment. So they may have, a backup core switch, but it is not kept in the same location as the core equipment. It's actually, it was a medium-based casino, and the spare core switch was actually on the 10th floor in storage, and the core equipment is based off of the basement in the elevator. And the network administrator with the financial individuals sat down, and they agreed that having the backup equipment in the same location as the primary equipment wasn't going to work for them. So they were okay with the cost of the downtime from moving the core equipment from the 10th floor to the basement when everything was down. That was a decision that they made. However, some administrators would not compromise. So the point here is understanding that redundancy, while in the network design phase, is extremely important. However, in practicality, it's not always as straightforward as we need to be able to do this. Normally, the person writing the check, or the individuals writing the checks, may not be okay with this type of equipment purchases. You may have a budget. There's other factors there than just being able to have redundant connections. So let's assume for a minute that our redundant connections are allowed because our administrator sits behind us and we have the budget. This brings up some other issues. If we have multiple links connected to the same switch or the same switching domain, we may end up with a switching loop. So to prevent this, we'd have to do some type of spanning tree protocol. If we were doing multiple links, because we have older switches, for example, and we need more bandwidth, we may do redundant paths or link aggregation. Again, that may cause additional issues, but we can solve them by being able to sit down and design the network ahead of time. So all of this helps to be able to reduce the size of the domain. Because again, when we're talking switching technologies, layer 2, we can be talking about either a broadcast domain or a collision domain. If we're using switches, collision domain is kind of going to be irrelevant because it's going to be based per port. However, our broadcast domains are going to be there because they are separated by a layer 3 device. So the goal here is to reduce the failure domains. And a failure domain basically is a module of the network. It is a well-designed network control that controls traffic and limits the size of any of the possible issues. For example, if a distribution switch goes out, that's going to affect, in our example, maybe one building. We can limit that by having 2 distribution switches there and having each access switch connected to both of them. That way, if one distribution switch goes out, everything will be switched to the second distribution switch. That way, there really isn't any downtime. So every router functions as a gateway for a limited number of access points. For example, multi-layer switches and routers are deployed in pairs. That way nothing is individual. But again, this is all based off of budget and business requirements. Each switch block will act independently of each other, and basically as a result, the failure of a single device should not affect the network, even if we're talking core layer devices. There should be 2 core devices, if not more. There should not be a single point or a single device that should affect the entire network, ideally. However, that's not always realistic, so do keep that in mind. How do we increase our bandwidth? First, purchase new switches. That's the easiest. And that's not always the easiest, but that's going to be realistically the longer term solution. However, switches cost money. Another way could be link aggregation. Link aggregation would probably be the easiest, assuming we have the enough free ports. The issue is In most businesses that I've worked with, there are not enough free ports to be able to do link aggregation, so that's been the issue. That's why I normally say buy new switches, typically because at that point we probably have already maxed out how many ports that we have available. So Ether channel definitely is going to be one of the feature tools. We can combine existing switch ports, assuming we have enough. We can configure them to work together, and that way we can do load balancing between these multi-links. We also have the ability to extend or extend the layer 2 access layer, and that would be by connecting access points to the access switches. Realistically, I've always seen this done at the distribution layer, not the access layer, but the access point itself will help to extend the access layer to wireless devices. This basically allows us to extend into different areas. Some of the considerations you need to have are looking at the types of wireless devices, coverage, interference, and if there's security considerations that have to be there. Are we allowed to have wireless devices? And again, that's going to be based off circumstance and your individual organization. So another thing we have to look at is our different routing protocols. There it goes. If we're using OSPF, for example, we need to be able to understand how OSPF works in multi-areas. Realistically, multi-area OSPF is outside the scope of the CCNA, so I always find it really funny when they talk about multi-area OSPF being a way to prune and tune our routing protocols, because yes, this is definitely a way that we could help control the flow of traffic. However, this is also way outside the scope of the CCNA. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.